Hi, my name is Asjad, and I am a graduate student at the University of Southern California. In this video, I will be giving a demo of a project that I built for the Data Science 551 course. The goal of this project was to build a data management and exploration solution for data of any domain. I chose the data regarding the positions of satellites orbiting around the Earth. The title of my project is Satellite Tracker. The application I built allows the user to visualize the real-time locations, historical orbital paths, and predicted orbital paths of artificial satellites. It also has the feature of locating and displaying all satellites which have a line of sight with the chosen location on the map, that is, the satellites which are above the horizon from that location. Before the demo, I will briefly go over the architecture of my project. So the technologies that I used were MySQL as the database, all the backend querying and processing done by PySpark, REST API is in Django, and frontend is in Angular. The first step of the project was to acquire data. The application data downloads data from two sources, spacetrack.org and the celesttrack.com. The first dataset is TLE and the second is SATCAT. TLE is an acronym for tool and element, which is a standard data format which contains the list of orbital elements of objects in orbit around the Earth at any given time. Then there are models which can then be used to calculate the location of the satellites with respect to Earth using these orbital coordinates. So I used the SGP4 model for this purpose in my project. The other dataset, SATCAT, is an acronym for Satellite Catalog, which gives metadata information, additional information regarding the satellite. This information includes the name, type, operational status, launch date, launch site, orbital period, etc. Both these datasets have a NORAD ID, which stands for North American Aerospace Defense ID as the primary identifier. NORAD ID is a sequential number assigned by the US Space Command to all objects orbiting the Earth. Since each satellite can be identified using NORAD ID in both the datasets, I used it to combine the two datasets. This data was then loaded to separate tables in MySQL after cleaning. Cleaning for TLE is done by Spark, and the first step is to filter the NORAD IDs 80,000 to 89,999 because these are reusable NORAD IDs assigned to temporary orbiting objects, also called analyst objects. For SATCAT, the data cleaning includes appropriate handling of empty or null values in columns which are used as lookups. So there are almost 10 columns, which I will show a little later in this video. PySpark was then used to calculate the current location of the satellite using RTD for parallel processing, and these locations were then written back to the database to a separate table. The front end mainly has these four components. And whenever an API call is done, where, for example, when a user asks for one or all satellites, PySpark actually joins the three tables on NORAD ID, that is the TLE, SATCAT, and location table, and aggregates the historical location of the satellites, calculates the current location of the satellite, and then returns the aggregated result. When the API to get the predicted path of the satellite is done, PySpark calculates the predicted orbital path in parallel and returns it. So I will now briefly go over the datasets before moving on to the UI. Here we can see the TLE data from the MySQL table. The TLE data was retrieved from spacetrack.org using the REST API in the form of JSON and was loaded to PySpark as a data frame. And after cleaning, PySpark loaded it to MySQL. So the TLE table has the NORAD ID and the time as the primary keys. The time is the time at which this data was retrieved. As you can see, it contains all the necessary orbital elements of the satellite, which can be used for position calculation like eccentricity, mean motion, inclination, etc. at this epoch. So using this information, we can calculate the position of the satellite at the current time as well as at any other given time. So the next table is SATCAT, where we can see the NORAD ID and time as the primary keys again. This is the time at which SATCAT was retrieved, and the NORAD ID for each satellite. And this shows and this data was retrieved in the form of CSV, loaded to PySpark, and then after cleaning, this was loaded to MySQL, and we can see here the metadata information like status code. So if the satellite is operational, decade, uh, country of ownership, like this one, Commonwealth of Independent States, United States, etc. Launch site, like for example, Air Force Eastern Test Range, Florida. Decay date, if the satellite is decayed already, a launch date, etc. So the third table is the location table, which stores the historical and the current locations of the satellites. This table has the NORAD ID and time as the primary keys as well, where NORAD ID is the satellite's identifier, and time is the time at which this position of the satellite was calculated, so latitude and longitude. To create this data, PySpark loads the latest TLE from the TLE table and only selecting the objects which have the payload type, so to exclude rocket bodies and debris, and then calculating the positions and storing in this table. And PySpark uses RDD and map function to compute all the satellites locations in parallel. So let's have a look at the UI now. So this is the homepage of the UI, which shows the list of actively orbiting satellites ordered by NORAD ID. I've also displayed the name and launch date of the satellite to give a little more information. So I can choose a random satellite from here and use this view on map button to display it on the map. Let's use this one. So now at the back end, once PySpark has calculated the current location of the satellite and then joined the TLE, SatCat, and location tables, it will return all the data from these tables with the historical locations of past 6 hours in an aggregated form. And then it will also calculate the predicted path of the satellite and for the next 6 hours. As you can see here, the current location and the orbit of the satellite are pretty clearly visible. The red line shows the satellite's historical path in the past 6 hours. And then satellite icon shows the satellite's current location, and the blue line shows the predicted path for the next 6 hours. You can also enable auto updates here using this checkbox so the location of the satellite starts getting updated in real time. You can scroll down and see the combined columns sorted alphabetically of the two datasets. We can see the launch date, launch site, Air Force Eastern Testing Range, all the other, like for example, the status is unknown for this satellite. Its period is 6751, and similar to all the information can be seen here. The next part of the application is search. So for search, I can either choose a specific column or I can do an all column search. So if a specific column is chosen, it will do an exact match search. If all is chosen, it will do like a substring search in all columns of all the satellites. So if I choose owner and type Italy here, so it's going to return all the satellites which have the owner Italy. So we get 27 results for this. Now, if I select all here and search for Italy again, although Italy is something that is highly unlikely to be in any other column, but this will also give an extra satellite in response. And the reason for that is that the ownership, the satellite is in joint ownership of France and Italy. So doing an exact match, that satellite was not returned. But if I did like an all column match, that satellite is returned in the result, like this one, France and Italy. So the all column is like a substring search. And similar to the previous view, I can click on view on map and it will show the current location, the predicted path, and the historical path of the satellite. I can also do a search like Navstar here. So Navstar is the name of the satellites, is in the name of the satellites in the GPS constellation. We can see this 74 satellites came up, and we can also view their locations using the button. So the next part of the application is the line of sight. So here I can choose any location on the map, and it will show all the satellites that are visible from that location. By visibility, it means that the satellites which are above the horizon and can potentially have a line of sight from that location. So let's click on Los Angeles. PySpark is now using RDD and a map function to calculate all the satellites locations, and it's calculating the altitude of those satellites from this particular location. And then it's filtering out the satellites which are below the horizon. So as we can see, there are lots of satellites which appear, and I can click on any satellite to view its name. I can also enable auto update from this page, so these satellites get updated in real time. Now I can click on any other location, such as anywhere in China, and it will show the satellites which are visible from that location. And not necessarily if a satellite is visible from Los Angeles, it is not necessary that it will be visible from China, right? So these are the satellites which are visible at this point in time from China. So something interesting to see here is that we have a series of satellites at the equator. So these are called geostationary satellites. and their orbit is in sync with the Earth's rotation. So they stay almost at the same place around for the whole day. So for example, China Sat-9, let's search this and view its orbit. As we can see, the orbit of this satellite has hardly left by the equator in the past 6 hours. And also in the predicted path, it's not going to leave the equator. So this satellite will always be visible from China. So this is a special kind of satellite, which is called geostationary satellite. So this was a brief demo of my project. I hope you guys liked my project and enjoyed this video, and hopefully this will fulfill the demo requirement of the project. Thank you.